Right, so trig equations that require factorization. Up to now, we've been looking at trig equations where we can always isolate the trig function on the left-hand side, and we can move the number term to the right-hand side. And then we've been finding the general solution from there. But that is not always the case with trig equations, and we're going to look at some equations where we cannot get the trig function alone on the left-hand side. And we're going to have to find a new method to solve them. Okay, we're going to have to just quickly think of our factorization. Okay, just to remind you, remember with our factorization, our first question is always, is there a highest common factor? If there is, then take it out. So like if I had k squared minus k, I would take out a common factor of k. And then remember, when you're taking a common factor out, you're actually dividing it back into each term to find out what we need to put in our bracket. So we're going to have k minus 1. Okay, so that's your highest common factor. And then we also have difference of two squares. If it's two terms. Or is it a trinomial if it's three terms? But most of the time we concentrate on this highest common factor because this is the one we're going to be using the most in trig. All right, so first question is always, is there a highest common factor? All right, so let's look at 6 sine squared alpha minus sine alpha is equal to 0. If you look at this equation, I cannot get sine alone on the left-hand side. There are two terms here, so no matter what you do, you're never going to get just sine alone on the left-hand side. All right, so because I can't get sine on one side and a number on the other, then I ask myself, okay, so 1. If you can't get one term alone on the one side and another term on the other, you make everything equal to 0. So you move everything to one side with a 0 on the other. So everything on one side and 0 on the other side. And then you try and factorize. And your first question, is there a highest common factor? If yes, take it out. All right, so let's look at this. I can't get just sine alone because there's two sine terms and they're not like terms, so I can't add them. So we make everything equal to 0, which is already done, and then we take out a common factor. All right, so this is like having 6k squared minus k. That's the same as that. And if we were looking at this, we would take out a k, and we would divide it into the first term and get 6k, and we divide it into the second term and we get minus 1. All right, so we can replace the sign with a k if you'd like to, or I'm pretty sure that you guys are going to be okay if I take out the sine alpha as the common factor. So I'm taking out a sine alpha as a common factor, and that means I have to divide the sine alpha into the first term, and I have to divide the sine alpha into the second term to take it out as a common factor. All right, and then you can see that you're going to end up with a 6 and a sine alpha left in the first term and a -1 in the second term. Okay, if you want to use a k's, you're welcome to, and then just go back and replace your k with a sine alpha so that we can keep solving. All right, once you've taken out a common factor, we use our zero product rule. So you have a product equal to 0. So we're going to say either the one factor is 0. Okay, so sine alpha is 0, or 6 sine alpha minus 1 is 0. So there's my zero product rule. Each of these products I make equal to 0, just like a normal factorization sum. Okay, now what happens is we have to solve each of these equations separately. So now do general solution to each factor. All right, so general solution to this one. Sign is positive. This is we assume that 0 is positive. Remember, to do the general solution, you've got to have your trig ratio on the left-hand side and your number term on the right-hand side. So this one is already set up. This one's already isolated. So for this one, we're going to go sign is positive. So we're working in quadrants 1 and 2. And then we find our reference angle. Alpha is going to be equal to sine minus 1 of 0. So my reference angle is going to be 0 degrees. All right, and then I go to quadrant 1, because I said I was working in quadrant 1 and 2. Remember, in quadrant 1, it's your reference angle. And in quadrant 2, it's 180 minus your reference angle. And then obviously plus your k-loss of 360. All right, so this is going to be alpha is equal to 0 plus k-loss of 360. And this one's going to be alpha is equal to 180 minus 0 plus k-lots of 360. Okay, so that's exactly what you've been doing over the last few days. We're just solving this one little side, and then we're going to go and we're going to take the other side and we're going to solve it just now. All right, so this is 0 plus k-lots of 360, and this one's just going to be 180 plus k-lots of 360, and we're going to have k as an element of z. Okay, now I need to take this side. All right, so I'm just moving to the next page quickly. And I'm going to take 6 sine alpha minus 1 is equal to 0. All right, so take each product, take each factor, sorry. And solve separately. Okay, so now this is a second factor, done the first one. So now we have to go through that whole thing. So here we have to usual rules. So we've got to isolate the trig function. So we're going to add 1 to each side. So we're going to have 6 sine alpha is equal to 1. Then we're going to divide both sides by 6. And now we have our trig function alone on the left-hand side, and this is 1 over 6. All right, again, sine is positive in quadrants 1 and 2. And then we find our reference angle. So it's going to be shift sign 1 over 6. Okay, so let's do that. Shift sign. And our reference angle is going to be 9,59. Okay, we said we were working here in quadrants 1 and 2. So in quadrant 1, we have our reference angle plus k lots of 360. And in quadrant 2, we have 180 minus our reference angle plus k lots of 360. This is already sorted. And 180 minus 9.49, sorry, 9.59 is going to be 170,41 plus k lots of 360. K is an element of Z. So this equation, because it was a zero product rule, has ended up with these two solutions here. So these would be that solution and that solution, as well as these two solutions from the other factor. All right. So there are 4 solutions. All right, so just going to make sure that you solve each factor. All right, let's try another one. Okay, so 2 cos squared theta is equal to cos theta. Okay, please if you can't get trig function alone, which you can't in this one, okay, then you always do everything equal to 0. Okay, so I'm going to have to move this cos theta to the left-hand side, and I'm going to have 2 cos squared theta minus cos theta is equal to 0. All right, once you have everything equal to 0, we ask ourselves, can I factorize? And here, there is a highest common factor. All right, again, you can, if you want to, make your cos into a k, take out your k as a common factor, and then replace your cos again. So you would replace cos theta there and cos theta there. Okay, so that is an option if you want to. Let me just do it here. So let cos theta is equal to k. So this is 2k squared minus k. Take out your common factor. So this will be cos theta and 2 cos theta minus 1. Okay. Okay, so I've just replaced that at the end there, and you can see how it's factorized. Right. Or we can go straight from here, and we're going to take out your common factor, which we're then going to divide back into each term. Okay, so what I have left in the first term, I have a 2 and a cos theta. What I have left in the second term, I have a 1. So you can use a k method, or you can just use your cos theta as a common factor. All right, what do we do after that? Well, we do our zero product rule. Okay, so this is just another way of factorizing. All right, so zero product rule. So cos theta equals 0, or 2 cos theta minus 1 is equal to 0. All right, there's my zero product rule. Now we're going to solve each part separately. Right, so with this one, remember we assume that 0 is positive, just to help us. So all right, so this is going to be in quadrant. Where is cos positive? It's positive in quadrant 1 and 4. Okay, and then we find our reference angle. Sorry, that's a bit messy there. All right, reference angle. Theta is equal to arc cos 0. And if you want to use your graphs, you can. If you don't know your graphs, then you would use your calculator. So cos of 0, 90. So my reference angle is going to be 90. Where was I working? I was working in quadrant 1 and I was working in quadrant 4. All right, quadrant 1 is your reference angle. So theta is equal to your reference angle plus k lots of 360. Quadrant 4, theta is 360 minus your reference angle plus k lots of 360. All right, so that's already sorted, and this one's going to be 270 plus k lots of 360. Plus k lots of 360. And remember, k is an element of z. Now, please don't forget to go back and pick up your other factor as well. We need to finish that. So don't forget to solve this. Okay, so we're going to go back and we're going to take this one. Just going to add a page. Oopsie. Okay, so the other one was 2 cos theta minus 1 is equal to 0. Okay, so this one, my trig function is not isolated, so we start by isolate your trig function, like we've been doing up to now. So we're going to add 1 to each side. And then we're going to divide it by 2 to get your trig function alone. Right, and then we ask, where is cos positive? In quadrants 1 and 4. And we find our reference angle. So it's going to be arc cos a half. Okay, so my reference angle is going to be 60 degrees. Where am I working? Quadrant 1 and quadrant 4. Okay, so remember quadrant 1 is going to be my reference angle plus k lots of 360, and quadrant 4 is 360 minus my reference angle plus k lots of 360. Okay, so that's finished. There are no like terms there. This one's going to be 300 plus k lots of 360. These are like terms. And then k is an element of z. And those are all our solutions. So again, we've ended up with 4 solutions. 2 from the cos theta is equal to 0, those 2 solutions. And then this one we solved here, and it gave us another 2 solutions from 2 cos theta minus 1 is 0. So each factor gives you 2 solutions, which we have to remember. All right, so those 2 were highest common factors. This one, because you do not have a 0 on this side, Okay, remember I said the first thing you do is you make everything equal to 0. All right, so please don't take out a common factor until you have a 0 on your right-hand side. Okay, so this one is a naught. Sorry, this one is a 1. So we can't take out a common factor. So the first thing you do is you make everything equal to 0. All right, so I'm going to take this. I'm going to minus 1 from each side to get a naught. Okay. Once you have it equal to naught, now you can factorize. And here, there is not a common factor because of that 1 at the end. Okay, so it's 3 terms. And let's do the k thing. So let cos x equal k. Let me do it up here. So we're going to have 3k squared plus 2k minus 1 is equal to naught. And once you've done that, or you probably could see the trinomial already, but here you can see that it's a trinomial, k squared, k, and your number. All right, so we're going to factorize. So we need factors of 3 and 1 that subtract to give 2. So let's 3k and 1 and 1 and 1. All right, so we're going to have, this gives me 3k, this gives me 1k, we want a positive 2, so it's got to be a positive 3 and a negative 1, which means that those go in one bracket and those go in the other bracket. All right, so we've got 3k minus 1 and k plus 1 is equal to 0. All right, so here, just let's double check. There's your 3k squared when we multiply the first two together. Then you get a positive 3k from those and a minus 1k from those, which gives you 2k. And then we have the negative 1 at the end. So double check your factorization. And then we use our zero product rule. So 3k minus 1 is naught, or k plus 1 is naught. All right, but remember that k is actually equal to cos theta, so I'm going to replace it here. Okay, all right, so now we have to solve each factor. Okay, so let's take, sorry, let me just go back to black. 3 cos theta minus 1 is naught, and the other one was cos theta plus 1 is naught. Okay, so there's my two factors. All right, so with this one, we need to isolate the trig ratio because it's not alone. So I'm going to add 1 to both sides. And then I'm going to divide by 3. So cos theta is going to be 1 over 3. All right, so cos is positive. quadrants 1 and 4. Reference angle. So it's going to be arc cos 1 over 3 and we're going to get 70,53 degrees. Okay, so quadrant 1. Remember, quadrant 1 is your reference angle plus k lots of 360, and quadrant 4 is 360 minus your reference angle plus k lots of 360. All right, so when we do that, we're going to end up with 289 plus k lots of 360. Okay, so those are the solutions from your 3 cos theta minus 1 is equal to 0. Right, now we pick up the second one and we do the same thing again. So we start all over. We isolate our trig function. And then we solve it. So cos is negative in quadrants 2 and 3. And remember, when we solve a reference angle, we do not include the sign in your reference angle. Okay, so arc cos of 1 would give you a 0. So my reference angle is a 0. And which quadrants are we working in? We're working in quadrant 2. And we're working in quadrant 3. Okay, quadrant 2 is your reference angle. Sorry. Quadrant 2 is 180 minus your reference angle. So that's going to be 180 plus k lots of 360. And quadrant 3 is 180 plus your reference angle. Okay, in this one, you can actually see they turn into the same solution. They're both 180 plus k lots of 360. So if you wanted to, you could just leave the quadrant 2 solution and not worry about the quadrant 3, but there's no problem having both of them. So there we go. There's our 4 solutions to that equation. All right, so it's up to you how you want to do it. If you can see your factorization without using a k, that's fine. But if you can't, replace your trig ratio with a k, factorize it, and then put your trig ratio back and keep going.